Hello and welcome to another video. In this video we're going to be working on number complement, and in this one the complement of an integer is the integer you get where you flip all the zeros to ones and all the ones to zeros in the binary representation. So 5 in binary and its complement, so 5 is 101, and flipping you just flip everything so it looks like this. This is 2. And then 1 in binary is a 1, so you just return 0. So let's talk about some basic binary things. Basically, like, what is binary? So binary is just, like, if you think of in decimal, we have some numbers like this, right? So these digits, let's actually make it an array, make it easier. Okay. And I wonder if I can flip it. I don't think so. Okay, let's actually write it like this. So 0, 1, 2, 3. Okay, so let's say we have a number like this. So this is like the zeroth place, the 1 place, the 2s, and so on. So if we have some just normal number like this, all these digits are 10 to the what power, right? So this number is 10 to the 0, this is 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. So if we have this number, we can get this number by saying, well, it's just going to be 5 times 10 to the 5th plus 4 times 10 to the 4th, and so on and so on and so on, and then that together would build this number. So it's exactly the same thing in binary, but in binary all you have is ones and zeros. So let's say we have a number like this. And similarly in binary, if we have a number that's 1 here and all zeros here, we don't really care about leading zeros, just like a normal decimal number, right? Like if we have this, we don't care about the leading zeros. Same thing with binary. So let's say we have a number like this. So this number is basically equivalent to 5 times 2. So the only difference is this is in decimal, it's 10 to the power. So this is 5 times 2 to the 5th plus 4, or it wouldn't be 5. It would just be the bit. So it'd be 1 times 2 to the 5th plus 0 times 2 to the 4th plus 0 times 2 to the 3rd plus 1 times 2 to the 1, oops, times 2 to the 1 plus 1 times 2 to the 0. And so this whole number would just be 2 to the 5th, which I think is 32. Yeah, so it's 32. This is the 16s. This is the 8s. This is the 4. So we have 32 plus 4 plus 2 plus 1. And so this number represents 39, I think. Maybe I did the math wrong. Basically, that's how binary works. So in binary, there's a couple things you're going to want to know. One is bit shifting, and the other is doing like ands and ors and so on. So ands and ors in binary are very similar to anding and ordering of Boolean. So if you have 0 or 1, you get 1. If you get 0 or 0, you get 0. Like you can basically replace these with Boolean values. So like true or false is true, and so on and so on and so on. So the only thing ORed with each other that would be 0 would be 0 or 0, because false or false is false. And then with and, it's the same as a programming and. So like 1 and 1 would be 1, because true and true is true. 1 and 0 would be true or false, because true and false is false, and so on. And then there's one more that's kind of important, is XOR. And XOR is basically XOR of 1 and 1 is 0, 0 and 0 is 0, and then 1 and 0 is 1, and 0 and 1 is this. So those are really the only ones you need to know. And then one final one is bit shifting. And bit shifting just means you take this whole number and you shift every single bit either to the right or to the left. So if I was to shift every single bit to the right, basically what that means is I just delete the last bit, and that's my new number. And I keep doing that. So, and then I just put leading zeros. And if I shift to the left, then all that means is I take all this and I move it to the left, and I just put a 0 here, and that's my new number. And that's the basic bit manipulation. So now, how do we solve this problem from all these things? So we have some number, and we can represent it in binary. So let's go back to our example. We can represent it in binary, but how do we actually get these bits? So to get the last bit of a number, you can do one of two things. You can say my number ANDed with a 1. And basically what that looks like is I have 1, 0, 0, 1, 0, 0, 1. ANDed with a 1, and a 1 is just all zeros and a 1. And like I said, the only time AND of numbers is a 1 is when you have a 1, 1, and 1. So if the last digit is a 1 and this is a 1, we will get 1. If the last digit is a 0, then we will get 0. So in this case, we just get this. That means the last bit's a 1. So you can get the last bit by doing that, anding it with a 1, or you can also do a mod 2. So if I do num mod 2, that will also give you the last bit. So it'll be 1 in this case. That's how we get the last bit. And one way to do this is we can get all the last bits and we could just like record them somewhere, write them down, and then flip them all and then like turn them into a number. But let's talk about some more creative ways. So basically what we can do instead is we can figure out how many bits are actually in the number. And like I said, every binary number, all the leading zeros don't count. So this number is really just this. And how do we figure that out? Well, we can just say while our number is non-zero, let's just keep adding bits to how many bits we have. So we can say like, we'll just increment the number of bits we have and we'll just like take our number and shift it to the right. And shift to the right looks like this. So we'll just shift it by 1 bit. So essentially what we can do is we can say like, okay, well, and you can do this a few ways. You can either do this. So in this solution, we basically say like, okay, so our bits is 1. We're going to shift our number to the right, which means just get rid of the last digit. 2 ways to do that. You either shift it to the right or you divide by 2. Either one works. So we'll say like we have 1 bit, then we have another bit, we shift to the right again. And then we have another bit, we shift to the right again. And then we have another bit and we get rid of this. So we have 4 bits total in that number. If we go back, that's the case, right? And then we could say like, let's just build that number then, and let's make that number all 1s. And the way to do that, so this is also pretty useful. So basically, if you know how many bits are in your number, because these are powers of 2, so this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, what we can do is we're trying to build a number that's all 1s, that's the same length as our original number. And the way we can do that is 2 to the bits minus 1. Because 2 to this bits will be 1, 0, 0, 0, 0. And then that minus 1 will be 1, 1, 1, 1. So essentially, that's how we can get a number that looks like this. Then we can do one of 2 things. So like I said, if you XOR a number with 1, it flips the bit basically. Because 0 XOR with 1 equals 1, so we flip the 0. And 1 XOR with 1 gives you a 0. So we can just build a number that's the same length as this and XOR them together. And then we will get 0, 1, 0, 0, which is all the bits flipped. Another way you can do that is notice that, so if we have this number, notice that our original number, let's call that x, plus its complement, all the bits shifted, let's call that y, will equal this all 1s. Right? Because in this number, some bits are going to be 0s, some bits are going to be 1s, but that added to its complement, which in this case will be 0, 1, 0, 0. Basically what you're doing is if the bit is 1, it makes a 0. If it's a 0, it'll make a 1. So when you add these together, so if I put it here, what's going to happen is every single one of these things is going to add up to 1 and there will never be a carry. So this will be like 1, 1, 1, 1. So if we know that, if x plus y equals this 1s things that we made it, then all 1s minus x will give us the complement as well. So these are kind of like the 2 ways you could do it getting this. Either XOR or this number minus this will give you the complement. Either way. And you could build this number either by doing 2 to the number of bits, or we can just say, instead of doing that, why don't we just keep shrinking this number, and every time we shrink this number, we just add a 1 to the number we build. So what that would look like is we start building a new number down here, and then we'll just say like, okay, well, we'll have a 1 here, and then we'll shift this to the right, and then we'll shift this to the left, and add another 1. And then we'll get rid of this, and we'll keep doing this, right? So for every number we delete, we add 1. And the way to add a number is, like I said, shift to the left and just add 1. And so at the end, you'll have this, and you'll have this. And then we can just say, okay, let's just take this number minus our original number, and that will be the complement. So hopefully that makes sense. A bunch of different ways to do it, but whatever you prefer, and hopefully it's like a little intro to bit manipulation. So we're going to do this last way I suggested. So what we're going to do is we're going to build this number full of 1s, so we'll call it 1s. And we need to save num because we're going to be modifying num to figure out how many bits it has. So we can just say like copy or something equals nums, or num. And we'll say while num is greater than 0, let's just keep adding a number to ones. And the way to do that is, like I said, you take ones, you shift it to the left, and then you add 1. Or you can AND it with 1, or it with 1. But hopefully that makes sense how these things work. Yeah. So we'll add 1, and then we'll take our original number and shift it to the right. So essentially we get rid of a bit from our original number and we add a bit to our new number that's a 1. Keep doing that until num is 0. Now all we have to do is just return num minus the copy that we made, and because num is all ones, the copy plus our original number will add up to it. So also important, if you do 2 to the powers and so on, I'll show this really quick. So these constraints are, oh, we screwed up. Okay, so 5, -5. So let's see what we did wrong. Oh, it's the other way, right? So copy minus num. Copy is the, actually, oh, this shouldn't be num. This shouldn't be, this should be ones minus copy, I believe. There we go, okay. So the other thing you want to be careful of is if you do that trick where you do the, here, or not that, let's see. If you do this, where I said like, okay, well, you can just do 2 to the number of bits minus 1. That the thing is there, you have to be careful because this number can go to 2 to the 31. So if you did 2 to the 32, that would give you an overflow. So you just have to be careful. If you do that, then use like a long instead. But hopefully this makes sense essentially. So for this 5, we're going to basically build a number. 5 looks like this in binary. So we're going to build this number and we're going to say, let's take that number minus 5, and that will give us the opposite. Or actually, I think I drew 5 wrong. 5 actually looks like this. So we're going to take that and subtract that. And this number actually is only 3 bits because 5 is only 3 bits. So it looks like this, and then we get this. Hopefully that makes sense now. So this is like our ones, this is our copy, and this is our result. Okay. And essentially the runtimes for all these things don't matter too much. So basically getting all the bits in a number is log of the number, because like a 32-bit number has 32 bits, you're getting a bit one at a time, so it takes 32 operations, which is log. Because basically anytime you get rid of a bit, you're dividing your number by 2, so that's logarithmic. So you can think of getting all the bits in one number as constant time. So getting all the bits in one number is constant time, and then this is constant time, so you can just say this is constant, and this is constant as well, roughly is, because you only have a 32-bit number, you don't have some huge thing. So it's just going to take max 32 operations. And yeah. So hopefully this is helpful, a little intro to bit manipulation, and then once we do harder problems, I'm going to assume you know these things. But for an easy one, I think it's fine to go into all this stuff. And yeah, that's going to be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.